Linear, quadratic, and exponential models. Our objective is to compare linear, quadratic, and exponential models, as well as, given a set of data, decide which type of function models the data, and write an equation to describe the function. Why learn this? Different situations in sports can be described by linear, quadratic, or exponential models. Let's look at the difference between a linear, quadratic, and exponential. So we have a training heart rate. So age 20, we have 170, age 30, 161.5, 40, 153, 50, 144.5. And notice how it makes a linear function. So it's a line. A quadratic is going to kind of come up and come down, hence a parabola. So you can look at the data here and see that that's what it forms. So when you look at a graph, you can notice what shape it's making. This one's making a line, so it's linear. This one's forming a parabola, so it's quadratic. This one is shooting off into infinity rather rapidly. So therefore, exponential. So now let's try graphing data to choose a model. So we're going to graph each set of data that's in the table, and then we're going to state which kind of model it best describes, whether that's linear, quadratic, or exponential. So when we plot the points, the top is the x value and the bottom is the y value. So let's plot these points. So we have our 0, 10, our 120, our 240, and our 380. Notice how it's coming up rather rapidly from left to right. So therefore, it is exponential. Let's try another one. Take a moment, pause the video, and plot these points on a grid. Then state whether or not it is linear, quadratic, or exponential. Now that you've had a chance to do that, let's see what we have. Well, after we plot the points, notice how it forms a line, so therefore it is linear. Another way you can use to decide upon what kind of model it is to look at the table itself. So we're going to look for a pattern in the sets of data to determine which kind of model best describes the data. So notice how the x values keep increasing at the same rate. So that lets us now go over to the y's. We look at our first differences. They're not the same, so it's not linear. Let's check the second differences. The second differences are the same, and when the second differences are the same, you end up with something that is a quadratic. That should sound rather familiar. We've talked about quadratic and linear and compared those two in previous lessons. So now we're simply just adding in the exponential piece. So once again, quadratic, the second differences are the same. If the first differences were the same, it would have been linear. So let's look at this next one. Okay, so our x values are increasing at the same rate, so now we can go over to our y's. Well, it's not changing as in adding or subtracting at the same rate, but we have a common ratio, so we keep multiplying by 0.85. So for every constant change of age of +1 years, there is a constant ratio. And when it's a constant ratio, we have an exponential. Let's recap. So a linear is y equals mx plus b. With a quadratic, it's y equals ax squared plus bx plus c. And then with an exponential, we have y equals a times b to the x. So when you look at an equation and it follows this format, if it follows this one, it's going to be linear. If it follows this one, it's going to be quadratic. And if it follows this one, it will be exponential. So now let's take a moment and look at a problem-solving application. We're going to use the data in the table to describe how the ladybug population is changing. And then we're going to write a function that models the data. So we're going to figure out whether it's linear, quadratic, or exponential, then write a function to state that. Once we have a function, then we can start to make predictions. Okay, so from 0 to 1, we're adding 1. Then from 1 to 2, we're adding 1 again. And then from 2 to 3, we're adding 1. So we have a constant change in our x values. Now let's look at our y values. To go from 10 to 30, we're multiplying by 3. To go from 30 to 90, we're multiplying by 3. And then we're multiplying by 3 again. So it's not a common difference, but it's a common ratio. So we know that it's exponential. Therefore, we want to use the form y equals a times b to the x. In our table, we have our x and y values. But when we finish filling out our formula and solving it out, we want to make sure we have a variable for y and x. But we need to figure out the a and the b first. So to do so, we're going to use our y and x values for one of them. I'm going to suggest 0 and 10, because 0 is a nice number to play with. So we're going to fill it in. So our y value is 10. We don't know what our a value is. Our b value is 3, because that's our common ratio. So there's your 3. And in this case, because we're dealing with this first one, so that way we can find our a value, our x was 0. So now we're going to solve for a and then rewrite our equation. So when we solve for a, 3 to the 0 is 1. So then we have 10 equals a times 1, which is the same thing as saying 10 equals a. So now we can fill out our formula. So we've got y equals 10 times 3 to the x. So there's our exponential function. The next piece it wanted us to do was to use our function to predict the ladybug population after 1 year. So we need to look at how our time is going. Our time is in months. So how many months are in 1 year? Well, that's 12. So our x value is going to be 12. So we have y equals 10 times 3 to the 12. And when we solve, we do 3 to the 12 first, order of operations, and then we're going to multiply by 10. And when we use our calculator to do so, we end up with 5,314,410 ladybugs after 1 year. And this concludes our lesson on linear, quadratic, and exponential models.